Welcome to the deep dive. Today we're getting into sorting algorithms, specifically one called selection sort.
That's right. And we're using some great material from Hello Algo as our guide here. It really lays things out clearly.
And our mission today for this deep dive is pretty focused. We want you to really get selection sort, not just what it does, but how it does it, why it performs the way it does.
Exactly. The goal is for this to stick with you, so you understand it deeply and can recall it years down the line, whether you're looking at code or just thinking about algorithms.
Because sorting, it's everywhere, right? Organizing emails, search results, it's fundamental stuff in computer science.
Absolutely fundamental. Even if you don't see it, you're interacting with sorting constantly. Understanding the mechanics, like with selection sort, is really insightful.
Okay, so let's dive in. The source material, Hello Algo, it starts with the core principle. What's the basic idea behind selection sort?
Well, the beauty of it, and Hello Algo points this out, is its simplicity. The core concept is
Yeah.
find the smallest thing left in the unsorted part of your list
Right.
and swap it into its correct final position at the start of the sorted section. You just repeat that.
Okay, so you're always working with two parts of the list in your head almost, a sorted beginning and an unsorted end.
Precisely. At any moment, you can picture the list.
Hmm.
Sorted elements on the left, unsorted on the right, and the sorted part just grows one element at a time.
I like thinking of it like maybe sorting a hand of cards. You look through the ones you haven't sorted yet, pick the lowest one, and you
Yeah.
place it down first. Then look through the rest, find the next lowest, place it second. Keep doing that.
That's a perfect analogy.
Yeah.
You select the minimum from the remaining pool each time. So let's walk through how Hello Algo breaks down the actual steps, the iteration.
Okay. Let's say we have n items in a list. To start, nothing's sorted. The whole thing, index 0 to n-1, is the unsorted section.
Right. So round one, the algorithm scans that entire list. From index 0 all the way down -1, it's looking for the smallest value.
And specifically the index of that smallest value, right? Let's call it k.
Exactly. Finds the index k, then it swaps the element at the very beginning, index 0, with the element it found at index k.
Ah, okay. So after that first swap, the smallest element overall is now sitting at index 0. It's sorted.
Correct. Position 0 is done. Now the unsorted part is smaller. It's from index 1 up to n-1.
Got it. So round two. Ignore index 0, look only from index 1 onwards, find the minimum value in that section.
Yes. Find the index of the minimum within the range 1 and let's say it's at index k prime this time.
And then you swap the element at the start of this section, which is index 1, with the element at k prime.
That's the pattern. Now the element at index 1 is correct. It's the smallest of everything from index 1 onwards. The sorted section is now indices 0 and 1.
And the unsorted part shrinks again, now starting in index 2.
And it just keeps going like that. As the source shows, in each round, say round I, you look at the unsorted chunk from index I to the n1, find the minimum there,
Find its index k.
and swap it with the element currently at index i's.
So you're locking in the correct element for position 0, then position 1, then 2, and so on. How many rounds does this take?
Well, you need to place n-1 elements correctly. So n-1 rounds of finding the minimum and swapping.
And after you've done that n-1 times, the first n-1 spots are filled correctly, the last element, it just has to be the largest, right? It's already in place.
Exactly. It falls into place automatically. The list is sorted. Hello Algo describes this with loops. An outer loop that goes from I equals 0 up to n2. That controls which position you're filling.
And inside that, an inner loop does the actual finding.
Correct. The inner loop scans from the current I to the end, n1. Its only job is to find the index k of the minimum element in that specific slice of the list.
So the inner loop finds k, finishes, and then the swap happens between index I and index k.
That's the process. Simple idea, repeated execution.
Okay, I think we've got a solid picture of the mechanism now. Finding the minimum, swapping it to the front of the unsorted section, repeat. But what does this mean for how it performs? Let's get into the characteristics.
Right. This is crucial. Understanding the how leads directly to the why of its performance. Hello Algo highlights three main things: time complexity, space complexity, and stability. Let's start with time.
And the source is clear in this. Time complexity is O(n)(2), big O of n squared.
O and 2, yeah. And the reason comes straight from those nested loops we just talked about. The outer loop runs like n times, roughly.
n1 times, technically.
Right, n1 times.
Yeah.
And for each of those outer runs, the inner loop has to scan the remaining part. First, it scans almost n elements, then n1, then n2, all the way down to just scanning 2 elements.
So lots of comparisons. The source even mentions the total number of inner loop comparisons adds up to something proportional to n squared. right? Like n1, n plus 2, 2.
Exactly. And that sum grows quadratically with n. So ON2. What that means practically for you is, well, it gets slow, fast, as the list gets bigger. Doubling the list size roughly quadruples the time.
Compared to faster sorts like, say, merge sort or quick sort, which are often n log n.
Right. ON2 is significantly slower for large inputs. And Hello Algo also calls it non-adaptive. What does that mean?
Does that tie into the ON2? Like it doesn't speed up if the list is already sorted?
Precisely. Non-adaptive means it doesn't care about the initial order because it always has to scan the entire remaining unsorted section to guarantee it finds the absolute minimum for that pass.
Uh-huh.
It does roughly the same amount of work even if the list was sorted perfectly to begin with. It can't take shortcuts.
Okay, so ON2 time, and it doesn't get faster on easy inputs. That's the time story. What about memory? How much extra space does it need?
Now this is where selection sort shines. The space complexity, according to the source, is O1, constant space.
O1, that's minimal, like almost nothing extra.
Pretty much. It only needs a tiny fixed amount of extra memory. Just space for a few variables to keep track of the loop counters, like I and J, and the index of the minimum element found K.
And that amount doesn't grow even if you have 1,000,000 items instead of 10.
Nope. Whether it's 10 items or 10 million, the extra memory needed is constant. That's what O1 means. This is why the source also calls it an in-place sort.
In place, meaning it sorts the data right there in the original array. It doesn't need to make a copy.
Exactly. It just shuffles the elements around within the existing memory space. No need for a whole new array. That's a huge plus if memory's tight.
Okay, so ON2 time, which isn't great for speed, but O1 space, which is fantastic for memory. What's the third characteristic Hello Algo points out?
The third one is stability. Selection sort is classified as a non-stable sort.
Non-stable. Okay, what does stability mean in sorting, and why isn't selection sort stable?
Stability is about what happens to elements that have equal values. A stable sort keeps equal elements in the same relative order they started in. Non-stable means it might change their relative order.
And selection sort isn't stable because of the swap, right? It can jump an element over another equal element.
Exactly. Think about it. In round I, you find the minimum element somewhere later, say at index K. You then swap numc and numsc.
Right.
If the element originally in numc was, say, a 5, and there was another 5 in between index I and index K, that swap could potentially move the minimum element found at K before the other 5 that was originally further ahead.
So if you had like 5A and 5B with 5A starting before 5B, you might end up with 5B before 5A in the sorted list.
Precisely. The values are still sorted correctly, all 5s together, but their original input order isn't guaranteed to be preserved. For some applications that matters, for others it doesn't.
Okay, let's pull that all together. We've got ON2, time kind of slow for big data sets, non-adaptive, O1 space, super memory efficient, in place, and non-stable doesn't keep equal items in their original order.
That's the profile. You have these clear trade-offs. The ON2 makes it generally unsuitable for, sorting millions of items if speed is your main concern.
But that O1 space is really appealing. You can see why it might be useful sometimes.
Absolutely. Hello Algo helps us see that balance. It might be slow in the grand scheme of things, but if you're working on a system with very limited memory or maybe sorting small lists where ON2 isn't that painful,
then its memory efficiency could make it a contender. It's about knowing these properties which stem directly from how it works to make the right choice.
exactly. Understand the why behind the big O notations and stability is key.
So we've really dug into selection sort today using Hello Algo as our map. We've seen the simple core idea, walked through the selection and swap steps, and unpacked those key traits: the ON2 time, the excellent O1 space, and its non-stable behavior.
And hopefully, by linking how it works, the repeated scans, the minimal extra variables, the long-distance swaps, to why it has these characteristics, this understanding will really solidify for you.
Yeah, getting the why makes it much easier to remember and apply. So building on all this, here's something to think about, a final thought based on our dive today. We know selection sort is ON2 time, but O1 space. Can you imagine a specific situation, maybe a particular type of data or system constraint, where despite its slowness, selection sort's extreme memory efficiency would actually make it the best possible choice? What would make you reach for it over faster sorts? Something for you to chew on.